No time for intros, this one is a brain melter. In episode 3, I proposed a novel optimization for Strassens, and today we're going to review its implementation and performance characteristics. If you're confused, go back and watch episodes 2 and 3, I'll have them linked in a card and the description. Let's go. First, let's start with what hasn't changed. We still use the same matrix addition and subtraction algorithms to do the additions and subtractions needed in Strassen's algorithm. We also use the exact same textbook implementation of multiplication for our base case. Now, on to the new stuff. First, you call this function, Strassen, with your matrices A and B, your pre-allocated result matrix C, and the size of a row in that matrix. Next, we allocate 3 empty matrices which will contain the rearranged A, B, and result. We then rearrange A and B, and then call the recursive part of the algorithm with these newly rearranged matrices. The result returned from the recursive part is also rearranged, so we must then perform the inverse rearrangement on it before returning it to the caller. Speaking of the recursive part, it's actually a lot simpler than last time. Here's the function before and after this change. First, the base case is exactly the same as last time, and in the recursive case, we still need to allocate the 2 temporary buffers and each of the 7 submatrices. After that, we start to see some changes. You'll notice that it no longer needs to copy from the arguments into the quadrant matrices and back, and is simply creating pointer aliases at 0, 1, 2, and 3/4 of the way through the array instead. This is all thanks to the rearrangement. To be totally clear, rearranging lets us replace this entire for loop with just these pointer aliases. The core of the algorithm is exactly the same as before. The 7 submatrices are computed identically, and the result matrix is also computed from the submatrices in the same way. The only difference is that this result matrix is now in the rearranged format. Now, let's go into depth about the rearranger, starting with the arguments. The first argument is the matrix we want to optimize, then the buffer that we're putting the optimized matrix into. Next, I and j represent where we are in this matrix in 2D space. Size is a constant, the size of the matrix, and cur is the current size at this level of recursion. The last argument is a pointer to where we are in the result buffer. This function is recursive, so most of these arguments are actually used to locate where we are in the matrix for each recursive step. As we continue to recur, we make smaller and smaller adjustments to I, j, and our result pointer to divide the matrix into smaller and smaller chunks. We keep track of how small these chunks are getting with the current size argument, and hit our base case once that's equal to our crossover size. Next, let's take a look at the base case. That's a really gnarly mem copy, but all you need to know is that it copies a 16 by 16 submatrix, 16 being our crossover size, from the matrix we want to optimize into our result buffer. All of the other variables just control exactly what submatrix we're copying and ensure it lands in the right place in our result. To figure out how we compute those variables, let's take a look at the recursive case. You'll see that this has 4 recursive calls, one for each of the 4 quadrant submatrices that we're continuously dividing. The first call handles the top left submatrix, the second the top right, then the bottom left, then the bottom right. That's how we get those recursive Z shapes from our last video. Finally, let's take a look at the changes to the arguments in the recursion. I is our vertical position in the matrix. The first 2 calls keep it at the top, and the bottom 2 increase it by half of the matrix's size, making it point at the lower half of the matrix. J controls where we are horizontally, and calls 2 and 4 increment it. The current size is always halved, since each submatrix has half the width and height of its parent, and the pointer into our result buffer is manipulated in such a way that the top left matrix goes first, then the top right, bottom left, and bottom right respectively. After all of that, we just return the result in the recursive case so the function has a nice API. The null in the base case is unused. The inverse rearranger works in the same way with similar arguments, except now we just use a single pointer into the rearranged matrix and our unrearranged result. We have the same 4-way recursive structure because we're trying to recursively reconstruct a big matrix out of a bunch of scattered quadrant matrices. Now a look at performance. Starting at size 64, we see an 18% speed up that grows to 44% as the matrices get larger. We also save exactly one matrix's worth of memory, which equates to 128 megabytes at size 4096. In addition, if an in-place version of this transformation were to exist, we would be able to quadruple the memory savings. That's not bad for a little bit of rearranging. Next time, we'll do a bit of macro-level out-of-order execution to further reduce our memory footprint. Until then, keep it tuned to Code Points.